Solve the following vector calculus word problem. Suppose that the vector A with components 1, 0, and 2 is written as the sum of a vector u in the direction of the vector B, which has the components 0, 0, and 1, and a vector v orthogonal to B. The length of v is. Okay, so the first step to solve this is to write all the information that we have in mathematical terms. So we have this vector A, and we have this vector B. And we know that the vector A is equal to the vector u plus the vector v, because it said is written as the sum of a vector u and a vector v. Now, what do we know about the vector u? So we obviously know what A's vector is, but we don't know u's. We know that u is in the direction of B. So we know that u is equal to some constant times by the vector B. And the reason why we have a constant times by vector B is because it must be in the same direction as B, so we can't multiply B by another vector, because then it won't be in the same direction as B, but we can multiply it by a constant, because we don't know to what scale this vector is, so we are simply multiplying it by a constant lambda, when lambda is an element of real numbers. Okay, so we now need to look at the vector V. The vector V is orthogonal to this vector B, so that means that V dotted with B is equal to 0. Okay, so if we wrote V out in vector forms, we have V with its x component, we have the y component, and we have the z component. And that is dotted with vector B, which is 0, 0, and 1. And the dot product is equal to 0. So when we're solving dot products, we multiply the x components. So 0 times by Vx is 0. And then we add the product of the y components. So Vy times 0 is 0. And then we also add the product of the z components. So Vz times by 1. So therefore we have that Vz times by 1, or just Vz, is equal to 0. So we solved for Vz. But we do know that Vx and Vy at this point in time can be any real numbers, because we don't actually know what they are, because we multiplied them by 0 and got rid of them. Okay, so that's all the information that we've got so far. So let's continue with this expression, knowing what we know now. So we know the vector A is equal to 1, 0, 2. So we have 1, 0, and 2 is equal to the vector u, which we've said is lambda times by the vector B, and lambda being a constant. So the vector B is 0, 0, and 1. So distributing lambda in here, lambda times by 0 is 0. Lambda times by 0, once again, it's 0. And lambda times by 1 is lambda. So u must then be 0, 0, lambda. And our vector V is, we don't know its x component, so we leave it in this form, Vx. We don't know its y component yet, so we say Vy. But its z component is equal to 0. That looks like a 6. There you go. 0. Okay. So now what we can do is we can add the x components of these two vectors, the y components and the z components, and equate that to this vector. So 0 plus Vx is just Vx. 0 plus Vy is just Vy. And lambda plus 0 is just lambda. So therefore we know that Vx, the x component of the vector V, is 1, the y component of the vector V is 0, and lambda is equal to 2. Okay, now the original question was, what is the length of vector V? So let's write out vector V now that we know it. Its x component is 1, its y component is 0, and its z component we solved over here. It is 0. So in order to calculate the length of vector V, we need the magnitude of vector V, which is equal to the x component squared plus the y component squared plus the z component squared, and that all square rooted. So 1 squared plus 0 squared plus 0 squared is just 1 squared, and the square root of 1 squared is just 1. So we know that the length of vector V is 1 unit. Thank you for watching.